Okay, welcome everybody to the second session. I'm very excited about this one specifically because we've been waiting for this for a year. So it's going to be very good. Last year, unfortunately, they couldn't come because of visa issues, and now we're very fortunate to have Anna at least here, and Ahmed also remotely. So a big round of applause for Anna and Ahmed.
All right, can everybody hear me in the back? Yeah, thank you. Okay. So my name is Anna. Thank you for being here. We have a little bit of a involved Zoom setup, so hopefully you'll excuse us while we switch back and forth. Ahmed, my colleague from MIT, is joining us on Zoom. He's going to do half of this presentation. And I want to say, we really want this to be an interactive thing, so please stop us at any point, ask questions. We want to bring as many of you along for the journey as we can. So yeah, let's sort of kick it off. Oh no, please work. Aha. All right. So automatic differentiation has really revolutionized many different domains in computer science. So we've seen it, have an impact on computational design and robotics, and within, computer graphics, inverse rendering has opened a whole new slew of applications that we can even talk about today. Possibly the most obvious evident example of automatic differentiation making a difference is within the domain of machine learning. And when we talk about automatic differentiation, what we're really talking about is gradient-based optimization. So the idea is you have some sort of loss. Oops. Oh, this is like... Okay, you have some sort of loss L that you're trying to minimize over some parameters theta, and the idea is that we want to use the computer to take derivatives of the programs we write. So you sort of specify your L as a program, and then you get the computer to compute these derivatives that you're then going to use for gradient-based optimization. Zooming in on just one of these domains, this is not collaborating. No. Okay, zooming in on one of these domains, machine learning, we see that automatic differentiation has had a specifically large impact on this field. And it's really been automatic differentiation in combination with graphics processing units that has allowed for this really rapid pace of innovation in this domain. And what really mattered for these techniques percolating within all of machine learning, basically, is that they were combined into these high-level layered systems that allowed you to write these layered architectures very quickly. And we saw over and over again that it wasn't really necessarily the peak performance of these GPU systems or their memory usage that mattered. What really mattered was the systems themselves and the affordances they allowed the users. So it allowed for really rapid iteration times, and it allowed users to really quickly experiment with a lot of these architectures. Meanwhile, in geometry processing today, the situation is that if you come up with a new algorithm, some new energy that you want to optimize, you basically have to derive these gradients yourself manually. And moreover, we're sort of completely incompatible with this whole machine learning ecosystem, right? So like the algorithms we come up with, the way we implement them, just don't really nicely plug into this large ecosystem. And so the thing we're going to try to do today is combine learning algorithms with classical geometry techniques. And we're going to try to do it in a way that we have the same amount of convenience and ease of use that the machine learning folks are really used to. And that means that we have to make our geometry algorithms differentiable. But sort of what does that even mean? What does it mean to differentiate a geometry processing? Unlike other domains, like machine learning, I can think of two ways, and we've come up with this sort of taxonomy for what it means to differentiate geometry processing algorithms. The first one is what we call differentiating for geometry processing, which means that we're trying to solve a classical geometry processing algorithm, but we're going to do it using a differentiable programming language. So we're going to get the computer to compute the gradients of our energy. And automatic differentiation, therefore, exists in service of solving the geometry processing problem. So to give you a concrete example, we can look at the sort of seminal as rigid as possible algorithm, where the problem is stated as follows. We're given some mesh in some neutral rest pose over here, and we want to deform it into this other mesh over here. And the way we do this is we specify a subset of the original mesh's vertices as the control handles. And then the user is free to take these control handles, deform them, place them anywhere in space, and the job of the algorithm itself is to solve some optimization problem that maps these control handles H to the deformed mesh. It basically like fills in the gaps for deforming the rest of the mesh. The optimization algorithm itself is solving this, constrained optimization problem. It's not really necessary that you get all of the details, but you can see that it's some sort of gradient-based optimization problem that we're trying to solve, and we're going to be doing it with automatic differentiation in this case. Right, we call this a forward problem for reasons that's going to become obvious very, very soon. But this was sort of differentiating for geometry processing. The other component of this duo is differentiating through geometry processing. And what do I mean by this? Well, now imagine you have a third penguin mesh. Maybe you've obtained it through some computer vision system that captures your penguin. This is like a real-life penguin, and you've taken a bunch of photos of it, and you've reconstructed it in 3D. And so now you have some sort of third mesh. This mesh can be completely different from your original mesh. It can have noise. It can have a completely different topology, for example. And now the problem you're trying to actually solve is you have your original mesh with these deformation handles that you want to sort of register to the other mesh. So the problem you're trying to solve is you want to find the set of control handles that moves this mesh such that it best approximates this target mesh. Okay, I see nods. Good, thank you. The way you can do this is you can specify some sort of difference between these two meshes, so some sort of loss, and then you're going to try to minimize this loss. We call this solving an inverse problem because it's kind of going the opposite way, right? In the first problem, we had the control handles and we got the deformed mesh. Here, we're trying to actually find the positions of the control handles. Now, the problem here is that in order to actually minimize this problem, you have to differentiate through G. And G was, remember, it was our solver. This solver can be really anything, right? In the context of as rigid as possible, it is like this custom bespoke algorithm that works really well, but it is really like problem specific. And so we're in this bind. Like, we don't want to throw away this awesome algorithm, but we also want to have some systematic way of differentiating through these problems. Maybe at this point, it's good to pause and ask, are there any questions? Is everybody following along? I know you're following along. Okay. Right, and this pattern is appearing increasingly more common in geometry processing. So each of these papers that's here has some sort of bespoke solution or ad hoc solution for the specific problem they're trying to solve. So we're not the first ones to come up with sort of inverting geometry processing algorithms, but what we're really trying to do in this talk is say that all of these problems can be unified into a concrete research program of its own. Now, for a little bit of the logistics, who is this course actually for? well, I hope there's a lot of geometry folks in this audience that are kind of curious about machine learning, maybe want to try it out a little bit, but still want to bring along all of their cool geometry knowledge and geometry techniques. And so this is really the main audience. However, we really also hope that this course can be more broadly interesting and introduce some techniques from geometry processing to the broader machine learning community. The course is going to have sort of two components. There's going to be theoretical explanations of everything, but we're really also going to try to make it very hands-on and practical, and we're going to try to, show you how to actually implement some of these algorithms. However, there are two prerequisites. The first one is that you're somewhat familiar with some sort of n-dimensional array programming language, so NumPy, PyTorch, even MATLAB should probably be fine. But we're not going to explain how to use PyTorch. And moreover, we do kind of expect some level of familiarity with just normal forward geometry processing. So we're not going to explain like what mean curvature flow is in great detail, and we're kind of expecting you to know that. Okay, so there are going to be two parts to this lecture, roughly divided into forward and inverse geometry processing. Yeah, I also want to use this opportunity to say that I'm very excited to announce that we're releasing a PyTorch library for geometry processing, differentiable geometry processing, inverse geometry processing. This has been in the works since I basically started my PhD, so I'm like very excited to be finally putting this out there. It's still being packaged up and put up on PyPI and so on, so it's not quite ready for prime time. But I wanted to use the fact that I have this audience today to sort of announce it. Please, start on GitHub, like, share, subscribe, all that good stuff. All right, so we can sort of move on to the first part, and I'm going to hand it over to Ahmed if I can figure out how to do so.
All right. So, yeah, thank you, Anna. So in this section, I wanted to give like a really brief introduction about automatic differentiation. And I want to be upfront here that like what we are going to do is very like gentle introduction. So the first couple of slides will feel like a material that you may have already know if you have ever worked on optimization problem. Like what is a gradient, what is gradient descent, what is a Jacobian, and this is on purpose. We want everybody at the beginning to be on the same place, to be familiar with all the notations that we're going to use for the rest of this course before we digging any deeper. So as you may know, a huge fraction of geometry processing boils down to minimizing certain energy function. So for example, if you want a smooth mesh, this is a minimization of some bending or Dirichlet energy. If you want a nice parameterization, this could be a minimization of some sort of distortion energy. If you want to deform a mesh that looks natural, this is also a minimization of elastic energy. So the notation we are going to use is theta is the thing that we are allowed to change is the optimization variable, like the vortex position could be the weight of some certain neural network, and the L is the scalar that we are trying to minimize. And we are mainly interested in using some sort of gradient descent to do this optimization. The gradient is just a vector of partial derivatives. It tells you how much L change if you nudge each parameter a little bit. So this vector usually like points to the direction of the steepest ascent. So the fastest way, basically the fastest way to go uphill. So if we want to minimize or go down, then we go to the other way. And we usually adjust this using a learning rate to avoid overshooting. And as you could see here, this movement usually is just a local movement. There is no guarantee that you're going to reach a global minima. And this is fine because most of the geometry processing algorithms are totally fine with finding a good local minima. A quick but important distinction here, because we're going to use this both words constantly for the rest of the course. When your function is just a single scalar value, its derivative is a gradient. It's basically a vector that have the same size as the input. But if you have if your output or your function is a vector valued function, then the derivative here is Jacobian. This is a full matrix, and the entry I, the entry I and j, will tell you how the output I it change when you wiggle or when you perturb the input j. And now if we look at this function on the left, if we look at this function on the left, each output here only touches 2 or 3 inputs. So for example, we have here F2 only touches theta 1, theta 2, and theta 3. This is because this is basically just a 1D mesh where vertices that are connected by an edge are the one in interact with one another. So the Jacobian in this case will become mostly 0. So each row here exactly will have 2 or maybe or just 3 non-zeros value following the mesh connectivity. Also the same story also appear if you have tetrahedral mesh or you have a triangle mesh where the Jacobian usually inherit its sparsity from the mesh itself. But we almost always don't want to build this or materialize this Jacobian matrix in memory. We usually want to apply this Jacobian with a vector product. And this has come usually in 2 flavors. The first one is the Jacobian vector product. You take the Jacobian, which is m by n, and you hit it from the right by a vector. So your vector here live in the input space. It have n number of entry, and the results live in the output space. It have m number of entry. And you should think about this operation as if I'm going to nudge the parameter along this direction, the Jacobian vector product tell you how the output move in this response. So the simplest case that I have here is where your vector is basically just the basis vector. So it's all 0 except only 1 as a first entry, which means that you are only going to perturb the one input, which is the first input of your function. And so in this case, again, vector Jacobian product is simply the direction derivative of the function along this direction. In general case, this vector could have non-zero anywhere, so the output in this case will basically just a weighted combination of the column of the Jacobian. And so we usually say that the Jacobian vector product pushes the perturbation forward. If we flip this around, we got the vector Jacobian product. Here the vector v live in the output space, so it have m number of entry, and it multiplies the Jacobian from the left. Or the way that you will usually see it written and implemented, we do the transpose. Now you transpose the Jacobian and multiply it from the right by a vector. It is the same thing, but now the results that you get from this operation live in the input space. That means that like the output will have n number of entries. And so in order to understand what it means to do like a Jacobian vector product, vector Jacobian product, we will use the sample setup where we have theta is our input vector here with m number of entry that goes into another function that produce f theta, which has m number of entry, and then k collapses all of this into a single loss. And so this is basically the forward path for evaluating this function, but we are usually interested into the other direction, which computes the derivative of L with respect to theta, which we could get using the chain rule. So with the chain rule, we start from the right with having dl by dk, which is basically the loss with respect to itself. So it is usually just 1. And then we take one step backward, which gives us dl by df. That is the seed that we started with here, multiplied by the Jacobian of k. So we could think about this operation or like just one backward path as basically just a vector Jacobian product. Now, if we take another backward step, we will have what we're looking for, the dl by d theta. Now, we take the row vector from the previous step, dl by df, and we multiply it by the Jacobian of f. So again, just a vector Jacobian product. And so as you could see, with every step, we apply just as a Jacobian to the sensitivities or to the sensitivity we get from the previous step to finally get the gradients that we are looking for. Okay, so this is why we usually say that the vector Jacobian product propagates sensitivity backward. So you start with seeding one as the loss or one as the output, and then this is flow back to the rest of the pipeline or basically the chain rule. And this is basically the foundation or basically the implementation of the reverse mode automatic differentiation. What we saw was just for a scalar loss. So generally, you might have an output that is basically a vector valued function. So we would need one backward pass for every output. So one backward pass for this one backward pass for this one backward pass for this one. So in this case, we usually say that the cost of reverse mode automatic differentiation is scale with the number of outputs in your function or on your problem. And the mirror image for this is the forward mode automatic differentiation. This is the Jacobian vector product we saw earlier. So instead of seeding the output, you start by seeding the input. And then we push this forward through the graph, and the output is the derivative of all the function with respect to one input. And so now if we want the derivative of all this output with respect to all this input, now we will have to take certain number of steps that is proportional to the number of inputs. So here in forward mode automatic differentiation, it will scale with the number of inputs in your problem. But almost in all problem, either in machine learning, in geometry, in other field that uses optimization, we almost always have ton of inputs and maybe very few outputs, maybe just a single scalar output or loss or energy. And so this is why we usually use reverse mode automatic differentiation, also called the back propagation, to compute derivative, because this is the most efficient way of computing the derivative. And so this is just a quick introduction to basic concepts that we're going to use later on. But we're going to write a few codes for this. But first, I want to check if there is any question on this part. Okay, I think we could move on. So the coding we're going to use here is very simple setup. We have a scalar function of 3 parameter, and we want this 3 derivative. First, I will express the parameter as simple torch tensors, and we will make sure to require PyTorch to trace their derivative. Otherwise, PyTorch will just treat this input as constants. And the function I'm writing here, which is this function, is just a simple Python expression. But behind the scene, every operation I have here, every multiplication, every summation, and so on, is being recorded in a graph for the backward pass when we compute as we compute the forward pass. And the actual gradient we are looking for is simply uses autograd.grad. We pass the input function and the 3 parameter we want the derivative with respect to, and it returns the 3 partial. And the order here is important. Grad 0, grad 0 is the df by the theta 1, which is the first input here. Here is also the same computation, but written in the way that you will see it maybe 90% of the time using the dot backward function. The difference here is where the gradient goes. So autograd return you the gradient right away. Backward deposit this gradient into the dot grad of the input tensors. So we could read it off as theta dot grad. And this is the recorded graph that you could get from PyTorch. The input parameter of this function is the leaf of this graph, and every operation is recorded as a node. And usually this is a very messy and complicated graph, but maybe for a simple function that we have, we could read it off. For example, like the division that we have here is this div backward, which is a function of theta and whatever this first term here. And one thing to notice here is that like the top nodes here are all are marked as accumulate grad, which means that the gradient are accumulated rather than being overwritten. So, and this is exactly why you usually start your optimization loop with optimizer.0 grad, because otherwise this gradient would pile up into the previous one. For a vector valued function, we have here just a simple function of with two parameters. So the Jacobian we will have here is should be 2 by 2. The only difference here is that I wrapped my function I wrapped my expression in a function because the autograd expected it to be a function, and then you input the input parameter. And what you get here is the Jacobian being dense materialized 2 by 2 matrix. As we mentioned, we usually want to do the product of this Jacobian with a certain vector. So the first one is the Jacobian vector product, which is just a GVP. The input here is just 3 input, the function itself, the point where you would like to evaluate the function, and then the vector with respect to which you would like to compute the Jacobian vector product. And what you get here is this is a product with and the PyTorch doesn't materialize or doesn't form this Jacobian at all. So this is quite efficient way to compute the Jacobian vector product. For vector Jacobian product, the other one, it works slightly differently. Here we're going to use the same autograd .grad function, but with an extra parameter w for the direction with respect to which you would like to compute the vector Jacobian product. And one thing to notice here before we finish this one is the theta here have to have the required grad, because again, vector Jacobian product is a backward or reverse mode automatic differentiation. So we have to tell PyTorch to deposit or like to track the derivative of this input, but this is not the case for Jacobian vector product, which is again forward mode, because it's a forward mode, so there is nothing here need to be tracked. So this is it for this chapter. I now will hand it over to Anna.
Thank you, Ahmed, for that lovely introduction to automatic differentiation as a concept. This part of the talk is really going to be trying to get our hands a little bit dirty with implementing some geometry processing algorithms in PyTorch using our new library called Iskra. And then we're going to try to use automatic differentiation to actually compute the derivatives of a geometry processing problem. OK, so the first thing we have to do is work through some basics and learn how to load a mesh. So the first thing we have to do is import PyTorch, because we're going to be using it all throughout the project. And then we're going to try to load a mesh. So the way we're going to do this is Iskra offers some nice utilities. So this URL-looking thing here actually pulls meshes down from Oded Stein's GitHub repository of meshes. So it's like a really easy way to get started. And we're going to take this koala mesh, and then we're going to extract the vertices and faces of this mesh. So this should look really familiar to you if you've ever used something like libIGL or GP Toolbox. These two objects that we have here are tensors. So this is a V by 3 basically matrix of vertex positions, floating point, and F by 3 number of triangles. And you can use Blender or Polyscope or whatever you want to visualize this mesh. So we got our cute koala. And now we're ready to do some actual geometry processing. So we can start off with like the most simple task, a little warm-up task, which is computing vertex normals. Now, the high-level problem we're going to be dealing with here at a conceptual level is that we want to do a bunch of sparse operations. So we have this, sparse matrix connectivity, and we're going to want to move data around this mesh. But we're using a dense programming language, like a dense tensor programming language, PyTorch. And so that is the sort of problem that any geometry processing system has to address. Iskra uses what we call a scatter-gather approach where the vertices, edges, and triangles are arranged into a sort of hierarchy. So we say vertices are faces of dimension 0, edges of dimension 1, and triangles of dimension 2. We think of, in this hierarchy, we think of edges as subfaces of triangles and vertices as subfaces of triangles and of edges. And on meshes, we can have data, be it scalar, vector, or matrix, living on any of these levels of the hierarchy. So you can have, vertex-based 3x3 matrices, for example, or so on. And the trick here is going to be figuring out, how do we move data around this hierarchy? Like what operations are allowed and supported in dense tensor programming languages? And B, where do we actually do our computation? And so in this case, to move data up the hierarchy, each face can collect data that's living on its on its subfaces. So in this context here, we say that the face is gathering, that the triangle is gathering all of the data living on all of the edges that constitute it. Similarly, a face can gather all of the data on all of its edges, and an edge can gather the data from its constituent vertices. To go the other direction, each face can scatter data down the hierarchy. So if you have something living on this face, you can take that value and distribute it, for example, to all of the edges here, or you can distribute it down to all of the vertices of this face, and likewise you can distribute edge-based data down to the vertices. This was very abstract, I am aware of this, so we're going to try to go back to our original example of computing normals. So here we have our vertex positions denoted in orange. So this is a 3-vector on each of the vertices here. And the first thing we're going to do to compute normals is a gather operation. So we're going to try to, each triangle here is going to gather on itself all of the vertex positions from all of the vertices that are that belong in that triangle. So now per triangle, we get three vectors of the vertex normals. And now we can use we have basically a tensor that has as many entries as there are faces, and each row of that tensor has three vectors. And so we can simply use standard PyTorch cross-product stuff to compute the per triangle normals. And now we have 3-vector per face, and we want to scatter that back to the vertices. We somehow want to transfer this information, distribute it to all of the vertices. So what we're going to say is we're going to do a scatter operation from the faces to the vertices. But now we've sort of encountered the problem, right? Like each triangle has more than one. Each vertex has more than one triangle incident on it. And so what do we do now? Well, the secret is that actually every scatter operation does an additional accumulation step. So it's not really a scatter operation. It's actually a scatter reduce operation, where this reduce can stand for a number of elementary operations like summing up or averaging or taking the min and the max of the values that you're transferring to the vertices. We're going to walk through how to do this in code, but I want to pause because I know this was really abstract and ask if there are any questions on this part. David.
This sounds like...
Oh.
So actually, I have two questions. The first one is, you said earlier that this is an approach to deal with the problem of sparsity. But to me, it sounds like this is describing something that's equivalent to sparse matrix multiplication or the like. So how does this fix the problem that we have sparse operations here?
It's not really that like we still want to do the sparse operations. We just want to express them nicely in a systematic way in a dense language. So you're taking these sparse operations and like we're giving you a computational framework for, it's going to become more evident when there's some code on the screen, I think. But we're trying to express the same sparse operations using only dense tensor operations, basically.
Does it make them more like GPU cache friendly or something?
Quite possibly, but it makes it much easier for you as a programmer.
Mm-hmm.
So, you know, I think, yes, implementing like sparse matrix stuff, which we actually did for this library, is possible, but there's a lot of operations that are really hard to, like very unnatural to express. You know, if you wanted to express this matrix, sorry, this vertex normal computation in matrices, I would find that personally very unnatural to do via matrices. So I think this mimics, it's like an alternative way of doing like a for loop around the vertex and summing stuff up.
Okay, and then the second thing was these reductions make a lot of sense when your underlying operation is commutative, like you just want to add things up at vertices or take the maximum or whatever. But sometimes I might want to take a vertex one ring and do some operation in the order in which things are glued around, say. Do you support that kind of ordered reduction?
Okay, this is a great question. So I think I have not experienced any sort of problems with this. Usually what it turns out is that like a lot of these operations that we think of, like do a thing per vertex, can actually be flipped around, and you can often say, you know, do a thing per edge and then redo something else. But no, I think that would be a limitation of this. I have struggled to find like a concrete example, but I'm happy to talk to you about this afterwards.
Thank you, Anna.
Any other questions? All right, so moving on to the actual coding portion of this. So we have our vertices and our faces, and the first thing we want to do, as we said, is gather stuff on the triangles. So we're going to want to take these vertex positions, which is a v/3 thing, and gather them onto the face. I find the scatter gather notation a little bit confusing personally. So in this I actually call this face indexing, because it's kind of like taking your data and indexing it with the face indices. And so we end up with a tensor that is f/3/3. So we said we would have 3 vectors per face. So that makes sense. And then you compute triangle normals. This is like an Iskra helper function, but it's basically, it's basically a cross product. And a normalization. And then the next thing we want to do is a scatter reduce. So Iskra offers this other function that is called reduce on subface. Here we're summing it up. You can average it. It doesn't really matter, because the next thing you're going to do is normalize. And so this is all the code you need to compute vertex normals in Iskra. And it's really short and compact. And I think sort of once you get used to this, it becomes very intuitive. So yeah, so you can. Oh, there's a question.
What is the verts.shape0 doing in your reduce?
That is just the number of vertices.
Okay, thanks.
So it's because you have your triangle normals, you have your face indices, and now you're trying to take this like f/3 tensor and map it to a v/3 tensor. So like this function needs to know what that v/3 is. Like it has no idea how many vertices you have. It could like take the maximum of the indices in the faces, but this ends up being a little bit more general. Right, so we've done that, and now we have our little koala guy with some normals. Yay!
Sorry to interrupt. Could you speak a little bit about any potential like memory efficiencies that you gain from your setup here?
Memory efficiencies?
Yeah.
I would say we like lose a little bit on memory. In particular, if you think about doing this indexing here with you like constructing the triangles, if you were to do this in C++ in like a very low level thing, you could just do a for loop, right? Whether that for loop would actually parallelize very nicely on the GPU is very questionable. I think Ahmed's whole research program has been trying to get stuff like that to work fast on the GPU. This actually ends up being very parallelizable in an embarrassingly parallel way. But yeah, you're definitely creating way more points than you actually need. We haven't actually noticed this be an issue in practice. We've done experiments with neural networks as well in our VRAM, and so we find this to be pretty tolerant. But like maybe if you're training a giant transformer and you're very memory constrained, maybe.
Yeah, because I was just thinking of the case in which you have like extremely high degree vertices, for example. I assume you're essentially going to be sort of multiplying the amount of things you have to store in memory by
high
degree.
Vertices. Like, what do you mean by that?
Oh, because like I mean vertices that are like connected that have a lot of edges, right? You're essentially splitting those up among individual faces and storing each of those in an individual memory space.
Like a factor of 3, right? With the number of faces.
Okay, thanks.
Okay, so this was sort of like a toy example. Right, maybe to add on to what you said there, I think this really does invite like a future line of research where you could still imagine writing code like that and then having a compiler that actually traces through these operations and lowers it into something more memory efficient. I'm not a compiler person, so like if you are, please get in touch. Yeah, it's a really interesting line of research. But our goal here was really to try to make this as intuitive as we can to use, and maybe at the cost of a little bit of memory efficiency, which is sort of the PyTorch design philosophy already. So let's move on to like a proper geometry processing problem, right? This was a warm up. So let's try to write down some variational energy, and then take a derivative of that using automatic differentiation. So here I have the area functional. This is basically some energy E. Omega here is our shape, our mesh, and what we're basically saying is like iterate over all of the triangles, take their areas, and sum it up. If you take the gradient of this energy and you do gradient descent with it, you end up tracing what is known as mean curvature flow. So it's basically thins out the mesh and looks something like, oh my god. This is really non-deterministic, which is why it's throwing me off. All right, it looks something like this. And there's multiple ways to think about this problem. Following with our normal computation, you can think of this as mean curvature weighted normals. It's not the same notion of normals as in the previous slide. Or you can think of this as applying, you can think of the gradient of this functional as applying the Laplacian to the vertex positions and then indexing at a vertex. Or you can think of it as the sort of integrated mean curvature multiplied by the normal. And then if you write down this ODE here and you solve it, you trace it, you basically do gradient descent on this energy, you get something that looks like this. Is everybody okay with this? All right, so we're going to try to implement this in Iskra now. So we're going to write down this energy, and we're going to use standard automatic differentiation and get this little koala with the mean curvature weighted, integrated mean curvature weighted normals. The first thing we're going to do, as Ahmed has taught us, is tell PyTorch that like we want to save gradients for this tensor. Like this is a tensor that we actually care about the gradients of, and so we sort of clone it to make sure we're not overwriting stuff, and then create a gradient tensor for it. Next, as we've done before, we instantiate all of the faces, all of the triangles, and then computing triangle areas again like a cross product behind the hood. but Iskra offers like a nice little utility. And so we compute the total area and then just sum it up. And then the thing we're going to do is call total area dot backwards. So this is, as again, Ahmed has taught us, it basically traces back down this graph of operations that we've done. So it does like a bunch of vector Jacobian products, applying it starting from our loss, which is the total area. It computes a bunch of vector Jacobian products until it reaches our original vertex tensor that we started with, and we can index into it using this vertices.grad. This vector that we get here is exactly the gradient that we wanted to get, right? So now, you know, if you're doing geometry processing, you have the first variation basically of your discrete energy, and you can now stick that into some time integrator and do maybe forward Euler with like a really small time step, which is not entirely great. So what people do in practice is they assemble a sparse Laplacian, and then you can take that sparse Laplacian. This is very familiar, again, if you've ever used libIGL or GP Toolbox. You assemble the sparse Laplacian and then apply it to the vertices, and now you've gotten the exact same vector per vertex. So if you walk along, you know, if you follow the direction of minus this vector, you're going to get that nice mean curvature flow. Again, this is sort of like getting this gradient directly is sort of like a forward Euler discretization. So what people actually do in practice is you sort of rewrite it, you rearrange stuff a little bit, and you get like a semi-implicit Euler. So you get this expression in the last row, which is the mass matrix plus some time variable, how far away you want a time step, plus your Laplacian, and then you solve that as a linear system with some right-hand side, which is your mass matrix times the vertex positions. I'm not going to go into more detail. The point here really is that it's really simple to implement something like this in Iskra again. Yes, David. Yes, this is all parallel and on the GPU. Oh, sorry.
I guess I can re-ask the question. It was whether this was being parallelized on the GPU.
Must I re-answer or? Yeah, so this is all, you know, happening completely. You basically specify where your data lives, much like you would in the rest of PyTorch, and it's all parallel and you know, you can seamlessly switch where you want the execution to happen. And so once you do that, you can sort of animate your koala again. But you know, we set out to do differentiable geometry processing, right? And so I've written a geometry processing program here, and naturally you would expect every step of this code that's here to also be differentiable. The very obvious question might be, well, there's a linear solver here. So like, how do we make that part differentiable? And that is going to be the question we're going to be dealing with in part 2 of this lecture. I'm going to check how we're doing on time, because what we were going to do is like a 5-minute break. Pretend you had a 5-minute break and wake up and join me again. The next part of this lecture is going to be on the adjoint method. The adjoint method is really what we're going to be using to differentiate through all of these solvers. Right. So the class of problems we're dealing with and the set of problems we want to solve is you want to minimize some loss L over some parameters theta. These parameters here, I just intend this to be like an abstract parameters vector, so nothing to do with meshes yet. And then we're going to have some function phi which maps these abstract parameters to values that live somewhere on the mesh. So this could be, you know, you have a long vector and you just say these points live here on the edge. You just sort of like remap them. It could also be something more complicated, right? Like theta could be the parameters of a neural network. And you could be mapping these parameters, you know, predicting vertex positions or predicting edge lengths or something like that. So like you get values that live on the mesh. And then lastly, we're gonna, in the midst of all of this, we're gonna try to solve some classical geometry processing optimization problem. And this is really gonna be the tricky part, is differentiating through this solver G. I'm gonna give this the output of G a name, so I'm gonna call this Y, to sort of differentiate between the fact that like G can be a non-differentiable thing, it can be like some, you know, God knows what iterative function that really we don't know a lot about, or we don't want to know a lot about. Like if you think about, you know, the low-level BLAS RPAC libraries. So we're going to give the output of this at optimality a name Y. And you know, specifying this optimization problem, the thing we actually really care about and need in our life is dl over d theta. So this is the gradient direction that we're going to be stepping in to solve our optimization problem. Okay, high-level recap picture. You have some solver G taking in some variable x and giving you some variable y. You want to differentiate through this. G is maybe not differentiable, maybe really complicated. Maybe it's like a Newton solver or a gradient descent procedure, and you don't actually want to step through, you know, a bunch of steps of this optimization procedure. If you do this via the VJPs, you know, the backward mode automatic differentiation, you're going to have to store a lot of stuff in memory, and it's going to become really inefficient. And so the contents of G, however, are actually not really important for us. What is really important for us is the relationship between x and y at optimality. So this relationship we can specify with a different function, f, which we say is going to have to be 0 at optimality. So like f of x, y is going to be 0, where y is the solution of our optimization G. How does this help us? Well, we're going to use some high school calculus tricks to actually use this function f to construct a derivative of y with respect to x without ever having to go through G directly. So we have two variables, f and x, and what we're going to do is pretend, under certain mild conditions, that y is a function of x. Once we, you know, this doesn't actually have to be the case. We don't have to have an expression of y as a function of x. But if we write this down, we can sort of just say, well, you know, we know this is the case, or we want this to be the case really, really badly. And then you can apply a total derivative with respect to x and, you know, expand that, and you get a chain rule with y. And then you can sort of reshuffle things around. And now kind of like a magical thing happened is that we wanted to take a derivative of G, but we actually ended up with an expression of the derivative of dy over dx completely without G. And as long as we can specify this equation f. And this is really, like, oftentimes this is the, you know, you might be wondering, well, why are we going this other route? But like, oftentimes you know what should hold at optimality, right? Like you've set out to solve some optimization problem, and you kind of know that like something should hold, like the solution to your optimization problem should have some properties. So let's try to walk through a more concrete example. Let's say our function g is a mapping from x to the upper half circle, right? Now this is really simple, and you can compute the gradients by hand, obviously. So this is just square root of 1 minus x squared. But kind of bear with me and pretend that this is something that's like maybe not differentiable, or like tries to avoid dividing by 0 in some way. Or maybe it's implemented in hardware and you can't really like trace all the operations using PyTorch's backward mode differentiation. The thing we're going to want to compute is dy dx. So that's basically this teal tangent line. which you can luckily see on the projector. I was worried about that. And then, you know, the way we're going to go about computing this is we have to specify some relationship f of x. But like we know this relationship because we know it's mapping to a half circle. So we know that the equations at you know, optimality in this case, or like at the solution, the equation of the circle should hold. It should be 0, right? So we can sort of map this implicit function is what we refer to these things. And now, you know, you can take this expression here, pretend y is a function of x, even though in this case it's, you know, it's just the implicit equation of a circle. Take the total derivative of this thing, plug in the values, and reshuffle things around, move things around to the other side. And now we have an expression for this gradient dy dx that is completely independent of the way we actually computed y. So it's completely independent of our g. And moreover, it only depends on these two partials, df dx and df dy, which I've indicated in colors here. So these are just two partial derivatives of f. Now, notice that a thing happens when we reach the end. I've put a little cross there. That is the mild condition I was talking about earlier. So that is the point where partial f, partial y is not invertible. So we can't just plug it in here, and otherwise it becomes degenerate at this point. So that is something to be careful about when using the implicit method. But you know, the big picture that I've already emphasized like 7 times is the separation of G and F. And so if you're like implementing an algorithm, you can really use this to your advantage. Questions? I see at least one person frowning in the audience. So I assume there are some questions.
Just wondering, when the conditions for the implicit function theorem break, are there any like milder assumptions that you could use on your function f, even if it's not inverted? Yeah, thank you.
All right, moving on to our example of that we had earlier. So we had this mean curvature flow thing happening, which is basically a linear solve, right? So you have this matrix. We're going to abstract it away. We're just going to call this part A, and this right-hand side, we're going to call it B. So we're just dealing with like a linear solve of some sparse linear system. So in this case, the thing we have is some solver. This could be conjugate gradient. It could be a direct solver. It could be whatever you wish. But the point is that it doesn't matter. And in this case, you know, in our notation df dx, our x is actually going to be two things. It's going to be a comma b, right? So it's just generalizing a little bit. So we have f of a comma b comma y. The thing that should hold at optimality is obviously that, you know, is the equation that we started with, the thing we're trying to solve. So it's just basically ay equals b, move stuff to the other side. And then we're going to want, this is just the expression of the implicit differentiation, we're going to want to compute like each of these independently. We're going to do it manually here for illustrative purposes, but if you remember, we have like a giant derivative taking machine at our disposal. So later in the talk, when Ahmed talks to you, we're not going to be computing these things manually. You're just going to use PyTorch to get these things. But right now, for illustrative purposes, we have, you know, our df dy is going to be just the matrix A, and then you can get the two different df dx's that look like this. Now, the one with respect to the matrix entries is really ugly, so I'm not gonna bother you with that one. But let's look at sort of the derivative with respect to the right hand side, right, like our b. So if we simply plug these two things into our expression up there, we get dy db. So we get the you know, derivative of our solution with respect to our right-hand side. So if you wiggle around the right-hand side by a little bit, you know you know, your solution y is going to change by this much. And it's going to change specifically by the inverse of your linear system. Now, we don't really just want this in isolation. What we actually want is to solve some sort of optimization problem, right? We started off, we have a full loss of some solver and some stuff, and I'm just going to, you know, our y in this case is going to be this expression that we started with. And again, we take the derivative of our loss with respect to our parameters theta, because that's where we want to do our gradient descent. You get this chain rule derivative here, and now we can plug in our A inverse into this expression here. And so we get this expression, right? And so this is basically the chain rule you have to implement to get, if you're trying to differentiate through a linear system with respect to the right-hand side, you have to implement this chain rule here to, in some sort of way, to basically step back and get the derivatives with respect to theta. You will notice that maybe if you look really hard, there's a giant A inverse in the middle of this. So that is actually going to be the really tricky part here, right? Like you have to, during your backward pass or forward pass, you have to solve another linear system. And going back to what Ahmed told us about, there's two ways to basically parenthesize this derivative computation, right? If you start and parenthesize from this side, you're basically computing the Jacobian vector product of this expression first, then you get another vector here, and then you're computing a Jacobian vector product here. On the other hand, it's very similar. You start off from your loss, you're going backwards, and you compute a vector Jacobian product. In this case, this vector Jacobian product is a matrix solve, right? Like you have a matrix inverse, and then you compute just a normal vector Jacobian product again. I've put the matrix sizes, the sizes of each of these Jacobians above the expression. And you will notice that like this parenthesization changes the actual computational demands of this algorithm, right? So if you're doing Jacobian vector products, you're first computing the inverse of the matrix that has, you're computing as many inverses, or like as many solutions to the linear system as there are parameters in your theta, versus if you start the other way around, your loss is usually a scalar, right? So you're only computing one linear solve solution. And so usually, you know, depending on your problem, but usually in our case, you really do want to do backward mode automatic differentiation. So you really want to use vector Jacobian products because they just save you so much time. And because this is so cool and so fast and like saves you so much stuff, people have given it a special name. They call it the adjoint method, which is like a phrase that used to scare me a lot until I just realized it's like high school math. So now you know how to differentiate through a linear system. I'm not actually going to walk through the inverse application. This is a figure from our paper on Iskra. The idea is basically you can invert mean curvature flow. You can step back in the opposite direction of mean curvature flow. If mean curvature flow thins things out, going the opposite direction with, you know, this isn't just normal going the opposite direction. There's like a bunch of regularization to make it look nice, to smooth it out. You get sort of like a mesh inflation thing, which I think looks kind of cute. Like you make your little mesh a little bit chubbier. So that's what I have for this section. Are there any questions? Yes, in the back. I can repeat it, I guess. Yeah, that's a great question. So the question was, have we ever run into numerical instabilities in the backward pass? The answer to that is it's the exact same linear solve as in the forward pass you're doing. Like it's the exact same matrix A. So if you can't solve your forward pass, or if you can solve your forward pass, you'll also be able to solve your backward pass. So this is just like something we leave to the user. In this specific scenario. In like the more general scenario, we do happen to encounter like poorly conditioned matrices, and it will be really interesting if you're solving something like inverse ARAP. Most of them will be really fast to compute, and then just occasionally you will get an iteration where you need like 3,000 steps to compute the backward pass. Any other questions? All right, we're running over time, so I'm going to hand it over to Ahmed.
Excuse me, I just had one quick question. Could you just explicit a bit this example? Because like, where does inverse, like where does differentiation comes from? Because like you can form like the inverse mean curvature flow without directly with the right sign.
Okay, because we're running out of time, maybe you can ask me about it later.
Okay.
It's basically you specify some sort of energy where you say like, I want my thinned out surface to look as close as possible to my original surface, optimize the vertex positions for that. We can talk about it a little bit later in more detail if you want. All right, Ahmed.
Okay, the floor is yours.
All right. So what we're gonna do in this section is that we're gonna try to write some code in PyTorch that allow us to differentiate through geometry processing algorithms that Anna has been talking about, and like how to use the implicit and the adjoint method to do this. So I'm gonna start with maybe something that everybody probably in this room have written before. This is the generic optimization loop. How the generic optimization loop in PyTorch looks like. You start by flagging off your optimization parameters that you require their gradient, and then you declare certain optimizer, and then inside your optimization loop for certain number of steps, you first zero out your gradient, and then compute the forward pass, compute a certain loss, and then you ask PyTorch to compute the gradient, and then you allow the optimizer to take a step. So the whole point of this section is to try to take this skeleton that we could use for any other problem and try to map it to write geometry layer or geometry processing layer in the forward pass in a way that is differentiable and efficient. And so we could try to map the general problems that Anna set up to us back to this to the skeleton. The first line loop over the first line here inside the loop will basically take theta, the optimization variable, map them to some geometric data x, and then x will become the input to our geometric layer, this geometry solver, and then we compute a loss and then backward, and then everything follow from there. So this entire skeleton looks the same as any canonical or any standard PyTorch codes that you might have written. The only thing that looks special or maybe looks different is this geometric layer. And the question now is like how to do it in a way that is differentiable and efficient in PyTorch. And so what might goes inside this geometric layer? So one example is this sparse linear solver, like this mean curvature flow thing. It could be stuff more complicated, like an eigensolver. It could be some certain local global scheme. And so the point is that like any like this geometric layer will involve some complicated, maybe complex, non-differentiable operation, or maybe non-differentiable in the sense that if you hand it over to PyTorch, it cannot compute the gradient in an efficient way. So to make things concrete, I think we're gonna focus on the case of having local step in a fixed point or iterative solvers. And so one first attempt is to let basically PyTorch trace is a solver. So you would write the loop in PyTorch where every step is differentiable and AutoGrad will handle it from there. And this could work really actually in principle, but the problem is the cost for this one is very high. because to run the backward, PyTorch will have to track all the intermediate state, like y1, y2, until you reach the solution yn. And so the memory in this case will grow linearly with the number of steps that you take inside this fixed point iteration, which is pretty wasteful, because we really don't care about like the path that we took in order to reach the solution. We care about the derivative around the solution itself, or the Jacobian around the solution itself. And this is like, and so the better abstraction or a better way to solve this problem is, as Anna mentioned, maybe in a different way, is to separate the forward from the backward pass. And this is the idea behind the implicit and the adjoint layer. So we will try to build such a layer in PyTorch and make it look for PyTorch like any normal PyTorch layer that is differentiable from the point of view of PyTorch. But internally, we will separate our forward from the backward pass. And so this will be implemented as a custom backward pass. And this splits our pipeline into two responsibility. Again, like in our general problem, phi and L will be handled automatically by PyTorch, because this is a simple function or simple elementary functions that PyTorch could easily track their gradients. And the complicated one, or maybe the one that PyTorch will do it inefficiently, we can handle ourselves using the adjoint method. And so this is the result that we just showed earlier for the using the implicit differentiation. The gradients that come out from the adjoint method is like the dl by d phi, the one we are looking for, is basically will involve two steps. The first one is that you solve for the adjoint variable lambda here. And then you take this lambda and then multiply it by the Jacobian of f with respect to x. So in order to solve like this adjoint method, there is only three partial derivatives that we are looking for. We're looking for dl by dy, df by dy, and df by dx. If we have the three parameter, or we have the three partial derivative, then we could implement this backward path in order to compute the derivative of L with respect to theta. And the way we will implement this adjoint layer is by building a custom layer in PyTorch. So if you don't know, like PyTorch allow you to extend the autograd by subclassing the torch autograd function, which require writing only just three static methods. The first one run whatever you want for the forward function evaluation. In this one, PyTorch doesn't trace any of the gradient of whatever happens here, which is exactly what we want. And then you set context. This is basically a place or a function where you could stash whatever you need in order to compute the backward pass. So in our case, we would like to store the input and the output of this implicit layer, because we're going to use them for computing the adjoint solve. And then the method that matters the most is the backward. PyTorch will call this with grad outputs, which is basically the gradient that is coming out to us from the previous layer in the chain rule. So in our case, this grade outputs is basically will be dl by dy. So inside here, this function, we will compute our gradient with respect to the input and with respect to the input and the return grad x. Okay, so in the next three slides, I'm gonna go through this three different partial derivatives that we're gonna compute, and we're gonna use PyTorch to compute it for us using using autograd. And the first one is this dl by dy, which what we need here in order to solve is the adjoint for lambda, the adjoint variable. This is basically just the right-hand side for this linear solve. But actually, we don't need to compute this one, as we just mentioned. This one just to come directly from PyTorch, like PyTorch should drop it to us in the backward method. So there is actually nothing to do here. So the next two partial derivative are actually the one we will spend most of our work. So the second one is the dy, is df by dy. which is basically measure how much the implicit function move if I wiggle or if I perturb the output y while fixing x to be constant or to be constant. Yeah. So we don't need to, and we don't need to materialize this matrix since we only need to solve for lambda. So if you're using a matrix-free solver, one where you only need the multiplication of the system by a vector, you could only do this by using a vector Jacobian product. So in code, we're gonna evaluate this implicit function once with x and y and require their gradient in order to flow through the solve. And then we're gonna use the autograd, the ones that we showed like earlier in the first section in this tutorial. And this will give us a df by dy multiplied by an input vector here. And so this will become our matrix-free operator. And then we could take this operator and feed it into any linear solve with that matrix-free. And probably if you are using a matrix-free solver, this means that this is an iterative solver. And a simple note to notice here about this linear solve is that we don't know if df by dy is symmetric or positive definite. And so in Iskra, we usually use gmres. But if it happens that you know for specific problems that you have that df by dy to be symmetric, positive, definite, or have any certain structure that you could leverage in order to make the linear solve efficient, then you should take advantage of this. For example, if it's like symmetric, positive, definite, then maybe a natural choice here is to use conjugate gradient. And finally, the last derivative is the df by dx. It is the same implicit function, but now we perturb the input to this implicit function and try to see how the output function will behave while fixing y. Again, we don't materialize this Jacobian because it's basically we only use it for another vector Jacobian product. And the nice part of all of this is the same implicit function that we used before. But the last time we differentiated with respect to y, now we differentiate with respect to x. And the input vector here for this Jacobian vector Jacobian product is the lambda that we got from the previous step. And now that we have all this three derivative, all of them matrix free, it means that for none of them we need to construct any Jacobian. And then this backward pass never touch, and also this backward pass never touches the internal of the solver itself. And so this is kind of an abstract way of like how we could think or how we could implement this. We're gonna put all of this in a concrete example, which is the inverse ERAB that Anna talked about earlier in this talk. So in the forward problem of the ERAB application, the ERAB basically takes the handle position and produces a deformed mesh where the solver figure out where every other vertex should go in order for the shape to bend naturally. And here C is basically all the constants that the solver needs. So this could include the Laplacian, which we need for certain steps in this in the ERAB. It could also include the resto position. So we take all of them and we just like represent them using C. Theta is the handle position. Phi is just an identity matrix, and J is the ERAB solver. And this will produce Y, which is the deformed mesh. Now for the inverse problem is about finding the handle, so the ERAB reproduces a target mesh. And one thing to be careful about here is that we are not choosing which vertices are the handle. This is set as fixed. We are only choosing where the handle should end up such that the final position when we run the forward path will give us the target mesh. And so this position now, this handle position now become our optimization variable for the inverse problem. And before we discuss the inverse problem, let us just recall the forward ERAB formulation, which is formally minimize the over both the deformed position and the per vertex rotation, the sum over edges, such that the deformed edges, edges differ as a pure rotation, or like looks as a pure rotation from the rest edges. And of course, we have two constraints, that the handle vortices are bent to the control handle, and the rotation should look like a rotation. So that means that it should live in the SO3. So this is basically an optimization in two variables, like in bare vortex position and the bare vortex rotation, which is complicated if we try to jointly solve for both of them. But if we fix it one, the other one become easy. And this is the idea behind Olga's ERAB local global scheme. The local step basically fixes the position, and for every vortex finds the best rotation independently. So this is a pure per vortex problem that we call fit local rotation, which you could build, or could easily implement using Gaussian scatter operation using Iskra, in addition to a normal PyTorch functions. The global step now freezes this rotation and try to find the position. And this boils down to just a linear solve here, with the constraint that the next position, the handle of the next position should bend to the boundary condition. So this step could be split to basically you assemble the right-hand side, and then you solve for a linear system. And then we alternate between these two steps for either a fixed number of iteration or until you converge. And so we could combine both of this local steps plus the global step into this function, ERAB step, which would take one iteration, which at every iteration it take u yk and return a new deformed position yk plus 1. So we could think about ERAB step as a function that takes the solver input and the current state and returns the next state. And when it converges, the output should satisfy this fixed point equation. And so with simple rearrangement, we could get this implicit relation, which we could then use for the adjoint solve. I will take just 30 seconds to stop to see if there is any question about this part. I cannot see people's faces if they frown, so Anna will tell me if anybody frown.
No frowns.
No frowns. Okay, awesome. All right, so here is how the forward path for our custom layer would look like. So first, we initialize the deformed mesh as a copy of the rest mesh, and we drop in the control handle in place. And then for certain number of iteration here, we're gonna call the ERAB step. Each ERAB step, again, it's the local global iteration. And then we keep track of the error. How much are we deforming? Like how far are we from the previous iteration? If the tolerance is less than, if the error less than certain tolerance, then we could exit, or if we exit, or we exhausted the maximum number of forward iteration. This is really like a really like quite a straightforward code to write. So now, and none of anything happens here has any derivative being tracked using PyTorch, which is what we want. Now we're gonna put all these three derivatives and the adjoint method in a code. So the first derivative is the grad deformed, which again, dl by dy that we get for free from the previous layer in the chain rule. The first thing we do is to retrieve the converged solution, like this y star, by running just one step of the ERAB and making sure that both the y and the theta have required grad, because for these two, we actually need the gradient to be tracked, but this is just for one step, because again, we want the derivative in the neighborhood of the solution, not for the path that gets us the solution. And now we implement this implicit function. Basically, this is just another vector Jacobian product that apply df by dy to any arbitrary vector. And now we hand this over to the linear solver. Again, this is our GMRes. And the output of this will basically be the lambda or the adjoint variable. Then the final gradient is just another vector Jacobian product. Now this is with respect to theta, and the grad theta is basically the gradient that we are looking for and which we return. And so,
Ahmed, we're just FYI, I think you can't hear, but we're at time. So like if you want to, oh, I'm muted. Can you hear me?
Yes. Oh, okay.
Just we're at time. So like if you can.
Let me march very quick along this. So basically, if we look back to this skeleton or standard PyTorch code, we will find that we actually could implement everything in this standard form. The only thing that will change is this ERAB step, which become this custom layer. And it works this is the rest position, and this is the target position, and this is the output of every outer optimization. And you could see here, the handle tried to squeeze and tighten such that it could reach the target position. And the good news is that all of this custom PyTorch layer, you don't need to write it yourself. All of this is packaged inside the Iskra. So everything almost that we talked about in this from section 3 and 4 could be shown boiled down to this just a single function API, make a joint layer. Basically what we told you about is basically what happened behind the scene inside this function. You give it the forward solver, you give it an implicit relation, and what is X and what is Y, and it does everything for you. It's a really powerful tool available in GitHub. So I encourage you to build something with it. Okay, so conclusion, I think I'm gonna just say at a high level, we just looked at what is the difference between differentiation and how differentiation for geometry processing is different, and this notion of differentiating using the PyTorch for computing the gradient for geometry processing algorithm, and differentiating through differentiating through geometry processing algorithm. We also did a little preview of the building block of automatic differentiation, and the most important one is the difference between forward and backward automatic differentiation. We looked at how to express geometry processing in the language in tensor, in the language of tensor language. And then we looked at the implicit differentiation and how we could put this in a code using PyTorch, and then we put everything together in one example, an end-to-end example, and that is available, or all these pieces that we talked about is available in Iskra. So I hope there is a time, but I just want to say that all what we did so far is basically one piece of this big landscape of differentiable system. That is I think exciting and growing. There is a lot of work in this domain. We have general differentiable programming system that is maybe for simulation and rendering. We have system for 3D learning and again differentiable rendering. And we have very few of them that started with TinyAD that was presented, I think, in SGP in 2022 and won the Best Paper Award. And after this, we have a couple of paper or couple of systems like RxMesh, Iskra, and Space, which I think all of them will going to be presented in SIGGRAPH this year. And I think there is a lot of work or exciting opportunity for as the interface between system design and geometry processing. And there is a lot of open problems that I think I'm gonna skip over, but I'm happy to talk about with you if you are interested in this interface between making things faster, making things usable in the same spirit of libIGL, but now with this modern technology or modern system or modern need for differentiable, making everything differentiable. With that, I would like to thank you so much for sticking around and everything we talked about, again, available at Iskra, and we look forward to your question if there is time.